Good morning, everybody. This is Heman Hassan, the tutor of organic chemistry from the University of Komar of Science and Technology, Department of Pharmacy. We are talking about the chemistry of alkene today. Alkenes are essential compounds in the structure of the drugs. Vitamin A is an example explained here that consists of several conjugated double bonds next to each other with a single bond. Let's get started and discuss about alkenes. The general formula of alkene is CnH2n. That means the number of hydrogen are double of the number of carbons, and the smallest alkene is ethylene or ethene, because we should have two carbons in order to have two bonds between them to represent the alkenes. The function group is the carbon-carbon double bond. As you can see here, I have a sigma bond and I have a pi bond. These two bonds will create a new class of hydrocarbons which we called alkene. If we have just a single bond, we called alkanes. The hybridization of this class of hydrocarbons is sp2. That means we have 3 sigma bond and 1 pi bond. The angle between each branch is 118, 18 and 121. We have a sigma bond and pi bond as we discussed. Firstly, the sigma bond will be created, then because of the overlapping of pz orbital, the pi bond will be created. Because the alkene have two bonds between two carbon, it gives a rigidity that doesn't allow the molecule to rotate around. So let's say this is carbon 1 and this is carbon 2. These two carbon cannot rotate because there is a double bond. If this carbon try to rotate, there is a force which forbid this orientation, while in that structure the orientation around the sigma bond is allowed. That is why in alkene we have cis and trans. Cis means beside, trans means opposite. That means the two groups with a high priority are on the opposite side, up and down. While here in the cis structure, both of the two higher priority groups are down or up. The IUPAC system of the alkene compound and cycloalkene compounds are the same exactly like the alkanes, except for alkanes we had ANE, but for alkenes we have ENE. Here we have cis and trans. Don't forget that. E means trans, Z means cis. That means the two groups are on the same side. Here in trans, the two groups are opposite to each other. If you have more than a function group, the longest parent chain is the one that cover both function group. So if you have a structure with two function groups, the longest parent chain is the one that covers both. Here is an example of the nomenclature of alkenes. If you look at the structure, you see that there is a double bond. So when we are trying to draw the structure, when we are trying to write the name of that structure, we should consider that the parent chain should include the double bond. As you can see here, in step 1 we have selected the parent chain, then we number the carbons, then the branch, then the name of the compound as explained here. I stop for a while in order to calculate it for yourself. Hope you understand very well. Let's go. Another example is 10.1 from your book. We have a double bond. If we select that one, we have 7 carbon, and on the other hand we have 8 carbon, but this is incorrect. Can you tell me why? Because the double bond is not in the structure. The double bond is outside the structure, while this class or family of the hydrocarbons is alkenes. So in the nomenclature we should cover the double bond. That is why we go for that, and this is wrong. Another example for the cyclic compounds. Always the cyclic compound has higher priority as long as the number of carbon of the cyclic compound will be bigger than the chain. So I have 5 carbon here. If I have 6 carbon outside, would I choose the 6 or 5? I would choose 6. No, it's incorrect. If the double bond will be in the structure of the 6, I will choose 6. If the double bond will be in the structure of the 5, I will choose 5. Even though if outside the ring I have 4 carbons, but including the double bond, I will choose the 4 and I will count the cyclic compound as a branch. We have some common nomenclatures. That means we have some alkene compounds that their name has been derived from the origin of discovery, or the first time that scientists have known it and name it. So butylene, isobutylene are the common name, but here we have 2-butene. While we have numbers, an illustration of the structure based on the branch and the number of carbons containing the double bond. Also the place of cis and trans, the geometry. This is IUPAC. But the other one, when we are saying isobutylene, it doesn't give a clear idea comparing to methyl propene, especially for the complex structure with higher number of carbons. How to select the cis and trans? How to count the E and Z in the structure? Firstly, create 2 carbon. That is the double bond. Carbon 1, carbon 2. Each carbon should have 4 bonds. So let's make it 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. Here I have a group. Also I have a group here. So if we count, this group is higher in atomic number. Okay, on the carbon 1. And let's go to the carbon 2. On the carbon 2, if I have this group with a higher atomic number. Now consider the place of the group on carbon 1 and the group on carbon 2. As you can see here, the higher priority group on carbon 1 is down, and the higher priority group on the carbon 2 is up. Remember, when we are saying higher priority, means higher in atomic number. Atomic number. Atomic number. Because they are opposite, we say T or trans or Z. Sorry, E, not Z. Trans E. Trans E, because they are opposite. If the 2 higher priority group are on opposite side, it is E, trans. But if the 2 higher priority on the same side, it is cis Z structure. So the E is for that, and the cis is for that. That means next to each other, opposite to each other. Hope it does make sense. The properties of carbon-carbon double bond. Firstly, there is no rotation around the double bond. Secondly, there is several stereoisomerisms like cis and trans. Thirdly, the stability of the trans is higher. Why? I have a big group here and I have another big group here. These two big groups are next to each other. They repel each other. While in the third structure, they are opposite. There is enough room here and there is enough room here. They are in relaxed position. No steric effect, no steric hindrance, no crowdness. So trans is much more stable than cis. As we explained it, we have Z from cis, from zusammen, that means together from a German name, and E from trans, from intigan, means opposite to each other. So let's recap a little bit about isomerisms. Isomer is the compound that have the same formula, same number of carbon, hydrogen, oxygen, nitrogen, sulfur, halogens, but different in structure. In structural isomers, there is different connectivity. That means these atoms, CHONS, halogens, have different connectivity over the overall structure of the hydrocarbons. And we have stereoisomerisms. Atoms have the same connectivity but different spatial. That means they are different in 3D rearrangement or 3D arrangement. Like I have a big group on the right hand side, but in the other structure I have a big group on the left hand side. In the 3-dimension structure, their connectivity is different. For the stereoisomerisms, we have geometrical isomers, which explain cis and trans, and Fasimer. This is correct for the organic compound. For the organometallic compounds, optical isomers are compound with non-superimposable mirror image. Non-superimposable mirror image. We explained that in the previous lecture. We have coordination isomers from the structural isomers. We said structural isomers have different connectivity. That means different in their atomic connection with each other. It's ligand and counter ion exchange places. And we have another type of structural isomers which we called linkage isomers. The ligand coordinate to the metal in the different ways. That means linkage between the metal and ligand is different. Coordination is the ligand and counter ion. We have discussed that slide before clearly, so I'm gonna skip it. What do we have? We called diastereomers. Diastereomers are cis and trans. Cis are next to each other in the first structure, and trans is the opposite one in the second structure. Let's take this example and explain it. On carbon 1, I have hydrogen and this structure. This is definitely bigger, up. On the other side, I have 2 carbon and 2 carbon. Do I have any preference? No. In that case, there is no geometrical isomers. What would you say about this compound? I have chlorine 17 and bromine 38 or 39 something. This is bigger, this is bigger. Trans. So let's talk about the bond cleavage. The bonds can be broken as a result of chemical reaction by heat, light, and solvent or catalyst. We have heterolytic cleavage. We explained it in the practical lecture. That means the bond unequally will break down. One of them will be a cation, like here. There is a cation in that structure because the 2 electrons of the bond go here, and there is a negative. But if you look at that structure, the bond will return to A becomes minus and B becomes positive. Positively charged ion, carbocation, and the negatively charged ion is carbanion or carbanion will be generated. Why? Because the bond between A and B is not broken equally. If it is broken equally, will result to A radical plus B radical. But here in this structure, if the 2 electrons of the bond goes to the B becomes negatively charged and the other one is positively charged. And we have homolytic cleavage. In homolytic cleavage, the bond will break down like that. Each electron has a radical. Free radical will be generated. What is carbonium ion? You know that IUM means positive. Carbonium ion is a positive carbon structure. In alkene, the compounds are sp2 hybridized. They are planar. What do we mean by planar? That means they are in 2D, not 3D. We have X and Y, not Z. At the cationic carbon center, the p orbital that is not utilized in the hybridized is empty and bearing the positive charge. We said it is sp2, the angle between them is 120 because they are planar. We have plane X and Y. We don't have a plane of Z in alkenes. We have in alkane, but not in alkenes. As you can see here, the empty orbital of the carbocation is perpendicular or stand on the 3 bonds in XY plane. So that is the X, that's Y. And the empty orbital is standing on the XY plane. Carbonium ion or carbocation is like that. it's empty with no electrons, and the 3 carbons are in the same plane, but that one is on the other plane opposite to the first plane. It's electron deficient, doesn't obey octet rule. What is octet rule? That means the atom in overall structure has 8 electrons. Before creation of the carbocation, carbon had 4 bonds. Each bond was a sharing of a single electron with another atom. As a result, we had 4 bonds. Each bond 2 electrons. 2 multiplied by 4, octet rule is obeyed. But now we have lost an electron. Doesn't obey octet rule at all. It is Lewis acid. If you remember, we explained it in the second practical lecture. Lewis acid is an atom with positive charge or deficient in electron. That means less electron, and we called electrophile. So electrophile, either it's a positive charge or deficient group or partial positive charge. They have sp2 hybridization. If the positive charge will form a new bond with another atom, we will have 4 sigma bond and becomes sp3. But if a pi bond will be recreated, it stays as sp2. The p orbital in carbonium ion is empty, can receive and accept electrons. All the ions are reactive because there is unbalancing in the number of protons and electrons. Deficient in electron, it is thirsty to get an electron in order to fill the gap, the emptiness. The stability of carbocation can be explained in detail here. We have discussed it simply before, and we will discuss it in advance here. So let's talk about inductive effect. What is inductive effect? Inductive effect means donation or receiving electron density from an outside source or to an outside source. Inductive effect is positive if we receive electron cloud or electron density from outside to in. Inductive effect positive, so means receiving electrons from outside to the carbocation. But also we have negative inductive effect. The negative inductive effect is donating or releasing electrons from itself, a negative charge mostly, to outside. For the carbocation, if we have 3 sources, 1, 2, 3, 1, 2, 1. If we have 3 sources to donate electron to fill the gap here, there will be most positive one. Secondly, if we have 2 sources of donation of electron to the carbocation, it's stronger. If we have 1 source to donate electron to the carbocation, it's less stronger. And the most least strong carbocation is methyl cation. CS3 positive. The factors that affect the stability of carbocation. Firstly, inductive effect. If you have a carbocation and donating electron from outside to fill the gap of the electron that has been lost becomes positive. If the groups outside gives electron to it, they will fulfill the emptiness of the positive charge and stabilize it. As you can see, the flashing is the donation of electron from outside to the positive charge, and it depends on the group. The group has an essential effect on the stability of carbocation. I mean the inductive effect group, this group. Here we don't have any group to donate electron to the positive charge. Here we have one. That means one source of stabilizing that positive charge by sending electron. Here we have two groups that send electron to the positive charge, and here we have three groups donating electron to the positive charge. Increasing carbocation stability by increasing the ease of formation. If the intermediate, the carbocation, will be most stable, it's easier to form. The reactivity of carbocation, as the carbocation is an incomplete octet, is sextet. Why sextet? Because we have a carbon 1, 2, 3 and a positive charge. 2 electron, 2 electron, 2 electron. 2 multiplied by 3 is 6. Sextet. Sextet is not octet, so it's not stable, but can be stabilized by the inductive effect. As long as the stability of the carbocation increase, the reactivity will decrease. As long as the stability will decrease, the reactivity will increase. Also, carbocation can rearrange, because we said the primary carbocation is stable, the secondary is more stable, the tertiary is the most stable one. So there could be an intermediate rearrangement in order to change the place of the positive charge from primary to secondary, or from primary to tertiary, or from secondary to tertiary. The first factor was inductive effect, and the second one is hyperconjugation. What is hyperconjugation? We try to explain it here. Basically, the positive charge with a neighboring bond will overlap. We called hyperconjugation. The third factor is the resonance. Resonance means exchanging the place of carbocation and the double bond. Hyperconjugation is overlapping the empty orbital with an orbital from outside the same carbon, on the same molecule, but outside the positive charge. If you can see the hyperconjugation, here it's explained, and here you can clearly identify. So here in the resonance we have just pi bond. Here we have pi and sigma. That's why we called hyperconjugation. So that's the difference between resonance and hyperconjugation. Hyperconjugation, it does include the sigma bond involvement, while the resonance is just pi. As you can see, the picture here is hyperconjugation. The empty orbital with a neighboring orbital will overlap. That is hyperconjugation. What are the factors are affecting the stability of carbocation? Delocalization means resonance. It's a factor that affects on their stability. These are the structures of delocalization. We have two formula, 1, 2 delocalization formula, but here we have 1, 2, 3, 4 delocalization formulas. This one is more stable than the other one on the top. The positive charges delocalizing into benzene ring increase the stability of carbocation. Why? Because in each of the states of the positive charge there is some time, and this creates a stability. If you have only 1 or 2 canonical formula, the probability of attacking that positive charge is high. But if you have 4 canonical formula, the possibility of attacking these positive charge is less. Here 50% possible to attack here, 50% to attack that position or that one. But in that structure, 1 position, 2 position, 3 position, 4 position. So it's 25% chance. Here is 50% chance of attacking. Another factor affecting the carbocation stability is the resonance. Resonance means delocalization of the pi bond with a positive or negative charge. If you can see here, we have a positive charge and a lone pair of electron. A lone pair of electron could be, or a pi bond could be in resonation or in resonance with a positive charge, like we can see here. The pi bond will create a double bond, and as a result the positive charge of here comes to the oxygen, like you see here. And the second one is carbanion. If you remember the previous slide, we have discussed about carbocation or carbonium ion, the factors that affect the stability, hyperconjugation, inductive effect, and resonance. Here for carbanion we have 2 factors affecting the stability of it. In the carbanion structure we have sp3 and the angle of the bonds are 109.28. The stability of carbanion ion is due to the resonance, stabilized by resonance or by inductive effect. That is the resonance, first factor of stability of the first factor of stabilization of carbanion ion is resonance. Resonance, we say that it's a delocalization of the pi bond with a positive charge or with a negative charge. The second factor is inductive effect. If you remember, in the previous slides we said that inductive effect has an effect on stability of the positive charge. With the same scenario but in opposite direction has an effect on the stability of negative charge. If you take a look at that example here, it's primary. Primary means one CH3 group. Secondary means two CH3 groups. Tertiary means 1, 2, 3 CH3 groups. And each of the CH3 groups will release electron. So let's consider that we have a negative charge and we have one source of releasing electron. That means from one source it gives more electron. It's negative. As long as the negativity here increase, the stability will decrease. I'm repeating it. It's a negative charge. As long as the negativity of this negative charge increase, the stability will decrease. So by that scenario, if we have one CH3 group is more stable than the 2 CH3 from 2 source 1, 2 negativity will be sent to the negative charge. So this negative charge becomes more negative by one source. This negative charge will be more negative by 2 source, and here by 3 source. In that case, this is the most stable. This is less stable. That's the less stable carbanion ion. We have free radical. For sure, negative charge and free radical has a planar or pyramidal. They have 7 electrons. If you remember, in the previous one we had 8 electrons for the negative, 6 for the positive. So C negative 8 electron, C positive 7 electron, C radical 6 electron. C radical is a representation of radical, 7 electron. It's stabilized by resonance or inductive effect. If you remember that for the positive charge we had a hyperconjugation, but here we don't have hyperconjugation, we just have resonance and inductive effect to stabilize it. Stability of the free radical and positive charge, these two, is by inductive effect or resonance. Okay. Inductive effect is releasing or withdrawing electrons from itself to the carbocation or carbanion. After that, we go into classification of the reagents. Nucleophilic reagents. Nucleophile means that negative charge lone pair of electron or enrich in electron. Attack the positive charge. Always from the nucleophile, the attack will be to the electrophile, because this is empty, this is full of electron. Okay, attacks the positive end of the polar bond, or nucleus loving now as a nucleophile. Nucleophile means negative, it loves the nucleus, that's the nucleus. Electrophile, nucleophile loves here, electrophile loves here. Generally, negatively charged or electron rich species or lone pair of electron are nucleophile. Like these molecules, they are nucleophile. OH, OCH3, CN, I, CH3, COO negative, NH2 negative, CH3 negative. And the other examples are explained here. They are Lewis base. Electrophilic reagents. Attacks a reagent of high electron density or electron level known as electrophile. Electrophile means E positive. Positive charge or empty orbital or deficient in electron. All positively charged or electron deficient species are electrophile. Neutral reagent, we have some reagents, they are not enriched in electron or not poor in electron. They are called neutral, like this. Or could be acid, could be base. All electrophile are in general Lewis acid. Preparation of alkene. How to prepare alkene? There are several reactions we use it to prepare alkene. Firstly, dehydration. Hydration means H2O from water, from alcohol by heat and acid. We can form the double bond. Also for the cyclic compound. Step 1 in the mechanism is protonation of the alcoholic oxygen. There will be an addition of oxygen to here to make better leaving group called good leaving group. Step 2, cleavage of the bond. Then this bond will be broken and called carbonium intermediate. It is possible to have a rearrangement. Then deprotonation from the carbon next to it. Then as a result, double bond will be created. Secondary and tertiary alcohols do elimination with the first order. The elimination takes place with the first order by the influence of one substrate. Water, OH negative attacking the hydrogen formed OH2 good leaving group, and the good leaving group is when there is a positive charge here, then deprotonation. Then we have OH2 and the double bond. OH3, sorry. Primary alcohols undergo E2 mechanism, forming the double bond. Dehydrohalogenation. Dehydrohalogenation means taking hydrogen and halogen from the RX to form R double bond R.